Hello everyone, this is Jana Zahid, and today I'll be explaining Lab 3 in Physics 2112. Um, for the introduction of this lab explored the behavior of DC circuits or direct current circuits, whether they were in series, parallel, and RC. And our key results were that in series, I1 equals I2 and the voltage split matched theory. For parallel circuits, the current split was based on resistance. And for RC circuits, we discovered that voltage followed exponential prediction. For the main physics concepts, of course, we have Ohm's law, which is V equals IR, Kirchhoff's loop law, which means that the sum of the potential differences in a loop equals zero, the junction rule, which means the current in equals the current out, and of course the capacitor equations. Our system was the battery, the resistors, the capacitors, and the wires, and our surroundings were air, lab table, meters, and environment. And our initial conditions were that the battery was at 3 volts and the resistors were at 47 ohms and 100 ohms. And we had a known UF for the capacitor. The purpose was to predict the voltage and current using laws. And we did that by analyzing the resistors in series and parallel, and we observed the capacitors charging and discharging, and we used multimeters to verify our predictions. So this is the series circuit observation, and this is the diagram. So we had the two resistors, and we predicted that there was an equal current, and V total equals the sum of V1 and V2, and the measured values confirmed this prediction. For the parallel circuit, the resistors in parallel were put in parallel with the battery, and our prediction was that the voltage was same across, but there were current splits, and the result was that there was higher current and lower resistance. For the RC circuit behavior, this is the diagram on the right, and for our setup, we used a resistor and a capacitor in series. And we have observed the capacitor voltage over time, and we matched the capacitor equation to what we had in the diagram. For possible error sources in this lab, they include internal resistance and contact issues within the components of the circuits themselves. There might be component tolerance within 5% of the predicted results. There might be issues with manual timing for the RC circuits, and there might be issues with the multimeter position limitations. For the similarities and differences between the model and real life, so of course Ohm's law is holds true in both. Conservation of energy is also true in both, and the current and voltage behavior is generally predictable using the model, and it's very close to the real life. But for differences, real ammeters have slight internal resistance that reduce the current by a small amount, and this is not shown in the model. And real batteries have internal resistance, and that may affect the voltage under load. And lastly, the ideal model allows infinite current, which is impossible in real life. Our first what if question was, what if you used a real ammeter instead of an ideal simulated ammeter? So we kind of touched up on this before, but basically the idea lies in that real ammeters have internal resistance, and although they're small, they can still change the current. And adding a real ammeter would slightly increase the total resistance of the circuit, and that would cause the current to be slightly lower than predicted. And the impact is minor but measurable, especially in low resistance circuits. And measurement accuracy depends on how calibrated the ammeter is and its resolution. For our second and last what if question, what if you charge the capacitor with a real battery and no resistor? So the ideal model predicts that instantaneous charging, meaning the voltage across the capacitor, reaches full value at t equals 0, or the start of the timing of the circuit. And this prediction assumes no resistance, which means that we have infinite current, and that's just not possible. But in real life, there's always some resistance within the wires, the capacitors, or the internal battery resistance, and a very high current would spike very briefly because it's limited by all those small resistances. And the capacitor would charge nearly instantly, but not really at the 0 mark, and could damage the battery or the capacitor due to this very large surge. And also, the real world behavior deviates sharply from the ideal model in this case, as infinite current is just not possible, and the current is not distributed at time equals 0. This is all for this lab. Thank you for watching. Thanks for listening, and I've learned a lot from this experiment.